You're watching GTV.
Good evening, and welcome to the second lecture in this summer's series of Heinz Pagel's Memorial Lectures. My name is David D. Young, and it is my pleasure to introduce this evening's speaker, Dr. Belinda Wilkes, who is the Associate Director of the Chandra X-ray Center in Cambridge. Dr. Wilkes' biographical sketch is in tonight's program, and so I will not repeat that for you here. You may read that at your leisure. But one small incident which is not in that biographical sketch was an event which perhaps threatened briefly Belinda's career in astronomy and astrophysics. Before she received her PhD from Cambridge University, she was enrolled in a Bachelor of Science program at St. Andrews in physics and astronomy, and in the course of her studies there she encountered at one time a large group of amateur astronomers. And these individuals were extremely conversant in the lore of constellations and naming them and the brightest stars in the sky and the functioning and virtues of various kinds of telescopes and designs. Well, Belinda, of course, was interested in the physics of these astronomical objects, much less than the nature of constellations and bright stars and telescopes, and so she was somewhat mortified to learn that she knew nothing of any of this lore that was being expressed by the amateur astronomers, and briefly thought that perhaps she was in the wrong field. Fortunately, however, she persevered, and it's our benefit that she did, and she's here this evening to speak to us about a very different kind of astronomy, an astronomy that is found in a new view of the distant universe with the Chandra X-ray Observatory. Belinda?
Thank you. Thank you, Dave. First, I'd like to thank the Aspen Center for Physics for their gracious invitation to come here tonight and speak to you. It is a pleasure to be here. And I've never been to Aspen before, and I've always heard about how wonderful it was, and it certainly has lived up to all my expectations. It's also a particular pleasure to be here to talk about the Chandra X-ray Observatory with which I work. With the inevitable and constant pressure of everyday work at the center, particularly with a satellite that's less than a year old, it is rare that I or anyone at the center, in fact, have time to sit back and think how exciting it all is to work with this wonderful observatory. And today, by coming to talk to you, I have that chance, and I plan to enjoy it. I will begin by introducing the X-ray Observatory, the Chandra X-ray Observatory, known affectionately by us as Chandra, in its role as the NASA's X-ray Great Observatory. I'll tell you about its launch almost a year ago now, and show you some of the images and scientific results that have been forthcoming in this first year. This is only a small fraction of the data from the observatory, because most of the data has been taken for specific astronomers who wrote proposals and won the right to design an observation, and they get to use it exclusively for a year to do their scientific analysis. Only then does it go into an archive which either the public or the rest of the astronomical community can use. So the pictures that I'm going to show you today come from the small amount of data that is already public, but was mostly taken for calibration reasons. But they're also useful scientifically, and members of the astronomical community, including ourselves, are working on them for the science as well, as you will see. This is an artist's impression of the Chandra X-ray Observatory as it looks right now out in space, with a very pretty nebula in the background. The nebula isn't really there, that's artistic license, I guess, to make it look pretty. But you can see, and this is a schematic that labels all the pieces. You won't be able to read them all, but I'll just go through the basics. These, of course, are the solar arrays that give it the power. At the front here, we have the mirror. And at the back end of the detectors, there's a door here which was opened once it was in orbit. It's called the sunshade door, which helps to keep the sunlight from the front of the telescope. So that's what it looks like. As I mentioned, it's an X-ray observatory. Now, when most of us think, even me, when I just think briefly of astronomers and looking at the stars, we tend to think of the astronomer in his backyard or her backyard with a telescope stuck to his or her eye, looking at the constellations, etc. Perhaps not so much in this day and age when we have large telescopes. Perhaps we think of astronomers on the top of mountains with big telescopes and computers to run them. But nevertheless, we tend to think of looking with our eyes in visible light. Visible light is only a small part of the electromagnetic spectrum, and I'm showing here the full range of radiation that we receive from outer space. And in order to get a full picture of any object, we really need to look at that object in all these wavelength ranges, from radio to microwave, infrared, visible light, of course, which we all know and love, the ultraviolet, the X-ray, and the gamma ray. Much of this end, the low energy end, can be done from the ground. Visible light can be done from the ground as well, or from high on a mountain. But to get ultraviolet, X-ray, or gamma ray radiation, we have to go above the Earth's atmosphere. That's just as well, because if this radiation reached the Earth, we wouldn't be here. We wouldn't be able to live if they could penetrate our atmosphere. So this is the high energy radiation with the shortest wavelengths, the highest energies. And this is where Chandra comes in. NASA has a suite of 4 great observatories, which are the biggest astronomy missions that NASA has funded. There are also a larger number of much smaller explorer-type missions, which some of you may have heard of. But these are the great observatories, very, very expensive missions. The one you probably have heard of most is the Hubble Space Telescope here, which is actually sensitive in visible light and ultraviolet. And the advantage of going above the atmosphere is we get a clearer picture because we don't have the atmosphere in our way. So it's still an advantage to go into space in the visible. This is the Hubble Space Telescope. This is Chandra in the X-ray. This picture is backwards from the last one, unfortunately, so the high energies are here. So Chandra was launched last July and has been working almost for a year. This is the Compton Gamma Ray Observatory, which has been in the news recently. It was launched several years ago and has been working very well, looking at very high energy radiation from the small number of sources that give you that. But recently it lost some of its control, some of its gyros, and NASA wasn't confident that it would be able to keep control of it. So there was a discussion about whether to bring it back into the Earth's atmosphere in a controlled way or to just let the orbit decay. And apparently there was a significant risk that this could hit somebody as it came down. It's a very big piece of equipment, so they chose to bring it down in a controlled manner. So this one is no longer operational. And this one over here is the infrared, Space Infrared Telescope Facility is its current name. It will be launched in December 2001. So it's in the final stages of preparation. The instruments are currently being delivered to be integrated to the satellite. So this is even with just these 3, this will be a very powerful suite of observatories up in space that will be working at the same time. Our observatory, the Chandra X-ray Observatory, was named for the Nobel laureate Subramanian Chandrasekhar. And NASA, with all its great missions, has a mission name like CERTIF has a mission name now. Chandra was called AXA, the Advanced X-ray Astronomy Facility. And when they're launched, they're given a name. And the name that ours was given was Chandra, after Chandrasekhar. This was actually, excuse me, the name was actually chosen in a public competition. Thousands of entries came from all over the country with, they have to be deceased people and preferably someone that has something to do with astronomy or space. So all kinds of names came in from all kinds of people. And the winner was selected from a panel of astronomers. And there was, I think, a teacher and a school girl who wrote the winning entries for, there were many other entries for this gentleman, but they wrote the winning entries, and they got a free trip to launch for that. So the Chandra X-ray Observatory was actually named 6 months, officially 6 months before it was launched, because the launch was delayed several times during the last year. And since it was a public competition and people wanted to hear the results, we named it a little earlier. It's also a very popular name, I think, with the community itself. He's a very well-known and highly respected theorist who worked at the University of Chicago for very many years. And anyone who studied astronomy as an undergraduate will know the name because he wrote standard textbooks on stellar structure and radiative transfer. The Chandra comes from the fact that by his friends and family he was known as Chandra rather than Chandrasekhar. So we call the satellite by that name. Here's another picture of the satellite. This is a schematic, again, and you'll recognize the solar panels, the mirrors in here, and the detectors at the back. X-ray astronomy is the technology of producing an image from X-rays is very different from the technology we're used to in the optical, where we look through a lens, like in our eyes or in binoculars or small telescopes. If you're used to that, you look through, and the lens focuses the light onto your eye or onto, in the case of a camera, for example, your photographic film. In the X-rays don't see a lens, they just go straight through it. The only way to focus them is by a grazing incidence. So the mirrors are actually sideways on. The X-rays come in at this end, and they graze off two pieces of very highly polished material here, and then focus way down here. There's a 10-meter focal length, so way down here on the instruments. So it's somewhat different than what we're used to. I won't show you many pictures of hardware, but this gives you a better idea of what the mirrors are like. This is the surface in here, inside the cylinder, and here's the polisher polishing it to a very high accuracy. This is just one of the mirrors. When they were put together, there are 4 mirrors that are nested within one another, and each one reflects the X-rays as they come through. The accuracy of the Chandra mirror is the largest technological advance in the observatory. It's the finest X-ray mirror that's ever been flown by at least an order of magnitude, and in fact it's the finest that will ever be flown in the foreseeable future, because there are no missions in the future planned that will have such high quality optics. This is a picture of the satellite at TRW in California. They were the prime contractor, and here's some people down here just to give you some idea of the scale of this. The telescope is here, and down at this end is what's called the Inertial upper stage, which was its rocket, which I'll tell you about in a minute, which sent it out into its orbit. Chandra was launched on the shuttle Columbia last July, the 23rd of July last year, and this is a picture of the crew with the shuttle in the background, taken at Cape Canaveral. It was in the news quite a lot as a shuttle mission because it had the first female commander. This is Commander Eileen Collins in the middle. Jeff Ashby was the pilot. Katie Coleman was the mission specialist in charge of Chandra itself. So she's actually visited us quite a few times up in Cambridge where we operate the satellite. Steve Hawley here was a veteran of many missions, but he was trained originally as an astronomer, astrophysicist. He has a PhD in astrophysics before he moved to NASA to become, I've forgotten the word, but anyway, to fly on his missions. So it's kind of nice to have someone up there who knows why we're doing this. Astronaut. Before he became an astronaut. This is a picture of the actual launch. If any of you, if there's anyone here who's never been to a launch, I highly recommend it. This is the only one I've ever been to, and it's really extremely exciting, particularly when your mission is sitting in the cargo bay. So last July, there was a mass exodus from Cambridge, from the Smithsonian Astrophysical Observatory, of everyone who could be spared, who didn't need to be there to operate the satellite once it was up, and who could afford to, went down to Florida to see the launch. And I went with my husband, who also works on the satellite, and my 2 children, who were at that time 7 and 5, and it was a really thrilling experience for us all. It was launched at 12:30 at night, and it was actually the 3rd attempt when it finally went. It was supposed to go the Monday, got down to 6 seconds, and then stopped dead, and everyone was holding their breath. There'd been some kind of sensor for a hydrogen leak. 2 days later, they tried again, and then there were storms, so we didn't get beyond 12 minutes. And then finally, on the Thursday night, it went. If anyone here was watching this particular launch, they might remember that it was actually very exciting even when it did go, because within 5 seconds of clearing the tower, we could hear over the tannoy, and we actually heard the live radio conversation with the crew from Johnson Space Flight Center, and they were telling them that things had gone wrong already too. The computers shut down, and of course there's always backup, so they switched in. And then it turned out there was a real hydrogen leak, and the shuttle was low in its orbit when it finally got into orbit. It got there safely, thank goodness, but it was somewhat low, so there had to be some adjustments to the schedule for releasing Chandra at the last minute, because the shuttle wasn't quite where it was supposed to be. So the first thing they did when they got there was release the satellite, because it's fractionally, well, I'll just show a picture of it higher up. You see how light this is? This is 12:30, it's dark, and it really looks incredibly light when it goes up. Incredible amount of power needed to get these things away from the Earth. So the first thing they did when they got up there was release the satellite. This is an artist's impression of what it looked like. Chandra was actually the largest payload that a shuttle has ever carried, and Columbia, which was the shuttle we used, was the only one that had a cargo bay large enough. Katie Coleman, as soon as they got up there, started the procedure of letting Chandra go. It was wound up, sort of out, as you can see, out from the cargo bay, and then released at a very precise time so that it would be able to reach the orbit that we were aiming for. Once it was released and she'd done her job, they were able to take pictures, and here's a real picture of it as it floats away from the shuttle, and it's actually going immediately into the nighttime, away from the sun, so this is a little bit in shadow. And this is the telescope itself, and this is what's called the inertial upper stage, which was its own rocket to boost it into the very high orbit that it is in now. And I'll show you a schematic of that orbit to show you why we needed a big rocket. The shuttle doesn't go very far away from the Earth, and we wanted the Chandra X-ray Observatory to be a very long way. And it's in an extremely highly elliptical orbit, and this point here is about 1/3 of the way to the moon. And the period of this orbit is about 3 days. So for most of those 3 days, we are clear of the radiation belts, which are indicated in red here around the Earth. This is the Earth. And we can observe. So that gives us very long periods of time when we can look at the source we want to look at without interruption. And then when we get into the radiation belts, we have to shut down the instruments to protect them, because otherwise they would get damaged by the radiation. And then when we come out again, of course, we turn them back on and start observing again. So it took about a week from the time the shuttle released it to get to its final orbit. Initially by the IUS, the inertial upper stage, which took it most of the way, but then it has some small motors of its own that adjusted the orbit to the final orbit, and we reached it very, very well. I mean, there was no problem with getting there. And then we all breathed a sigh of relief. Then began the procedure of turning all the instruments and making sure they still worked. So now, and they do. That's the good news, they do work. So now I'll move on to some of the science. And this is just a brief write-up of the kind of science that we do in the X-rays, specifically in the X-rays, and advantages that Chandra will give us. We can look at galaxy clusters. Now, the galaxies, like our Milky Way, tend to like to stay together, a bit like people do. They tend to form together in a group. And so when you look out in space, you see these great clumps of galaxies in the optical, clustered together. And it's very, very pretty. I'll show you an image a bit later on. They are actually the largest gravitationally bound objects in the universe. So they're like the main building blocks of the universe. In the X-ray, we're able to see the hot material in between the galaxies. And so we're able to observe the formation and evolution of these large-scale structures, and also to measure the amount of material. In order to measure the amount of material, we need to see it. And the optical gives us the galaxies, the X-rays give us the gas that are in these clusters of galaxies. We can look at quasars. These are close to my heart because this is a subject of my research. They're galaxies which are believed to have supermassive black holes right in their center that produce huge amounts of radiation over the whole electromagnetic spectrum. And they have jets coming out of them. So we can take pictures in the X-rays of the jets and of the very center of these objects to understand them better. We can look at supernovae, stars when they get old, run out of material in this, run out of fuel in their center, and they stop burning. And what happens is that the core collapses and the outer layers of the star expand catastrophically. and we get a very bright but short-term burst of energy. And then the material moves away slowly, away from the star that it started from over a long period of time. And they produce these beautiful supernova remnants, which we can study in the X-rays. In the X-rays, we see the very hot edge of the shock as it hits the material around about. I won't be talking today about stellar coronae, but with Chandra, we have gratings, and we can split the light up into into its various components, different energies, very, very accurately. So we can study the different elements in the corona of the stars. And that's much more accurately than has been done before. We can also take very, very deep pictures, much deeper than has ever been taken before in the X-rays, and look for new sources. Some of them we think we know what they're going to be, and I'm sure we're also going to be surprised as well. So I mentioned that the main technological advance of this observatory is its angular resolution, its ability to look in very, very fine detail. So resolve two sources that are very, very close together. It's a factor of 10 in one dimension or 100 in two dimensions better than the previous missions. It also can look much fainter, a factor of 10 to 100 times fainter than any previous mission. And it also covers the full X-ray energy range for the first time all at once, from 0.1 to 10 keV, for those of you who are familiar with that. That's 2 octaves in energy, which is a very wide band. We can obtain spectra across the supernova. We can look at the amount of emission in low-energy X-rays and in high-energy X-rays at any point in this image. So that can tell us a lot about how it's structured. And as I mentioned, high-resolution spectroscopy as well. Here is a picture, first picture I will show you, of the Orion Nebula in the X-rays. Now, the Orion Nebula is actually something you can see with your naked eyes. It's the central of the 3 stars, quote, in Orion's dagger. And it's better to see it with averted vision, but you can certainly see this little fuzzy blob. You can also see it in the X-rays. This is a picture taken with the previously best X-ray satellite in terms of spatial resolution, ROSAT, which actually was launched the same year as the Hubble Space Telescope, about 10 years ago, and is no longer operating, but operated very well for about 7 years. This was a picture of the Orion Nebula with ROSAT that took about a day, 47 kiloseconds. It's about a day to take. With Chandra, with about 1/3 of the time, this is the picture that we get. Actually looks a little blurry. I'll see if I can improve the focus. Sure I can. What we see in the middle is that here it's just a fuzzy blob. Here we have a fuzzy blob, but it's much smaller, and now we start to see some of the individual sources that make up the nebula. And then as we move further away, there are many, many more objects than there are in this picture. So it gives you some idea of how much better spatial resolution, the much sharper picture we have with Chandra. Here's a picture of a supernova remnant. This was actually the official first light image. It wasn't the first thing we looked at because we first had to focus the telescope, and I'll tell you the story of that a bit later. But this was the official first light image that we took for the press, if you like, Cassiopeia A in the X-ray, and this is a comparison with the optical. This is a supernova remnant, and you can see that the material actually moved right from the middle here, from this star in the middle that blew up, and all this material has moved out over the years, and it tends to form this kind of spherical shell. But you can see there's a huge amount of structure in here, very, very fine detail that we can now study with Chandra that we weren't able to do before. The optical picture is much less dramatic. You see just a few little wisps here, here, and here, and they're not as far out as the X-rays. So it's very clear that in the X-rays we're seeing the hottest gas right at the edge of the shock front, where the material is hitting the interstellar medium further out. And in the optical we see much cooler material. It's further back. It's been shocked for a while ago, and it's cooling down now. This also illustrates the power of seeing the optical and the X-ray together, because we're able to see where the cool material is and where the hot material is, and then study it in more detail. With just this image too, this particular detector has energy resolution and can give you a rough spectrum. So here's the same picture here. And on this side, what we've done is collect the counts from a region here and spread it out over energy. This really isn't focused very well. And the shape of this spectrum here is just the response of the detector. It's much better at finding 2 kilovolt X-rays than 0.1 kilovolts or 8 kilovolts. But these lines here are real emission lines due to various elements that are present in the supernova remnant. There's iron, calcium, argon, sulfur, silicon, magnesium, neon. These are metals. And the importance of supernovae to the study of the universe, if you like, is that they're the way in which these heavy elements, which are produced in stars, inside, deep inside stars, and are necessary for the formation of life, like us, they get into the interstellar medium and then into planets and therefore presumably into people and other kinds of life via supernovae. So it's very important that we understand how this material is spread out and what kind of conditions it's under, and we can study this spectrum as a function of position around this nebula in order to understand that. In order to see, if you like, the origin of life. This is the initial origin of life in the universe. With the gratings, I have a picture here just to give you some idea of what you see with a grating. This is another supernova remnant. It's much smaller, but you can see it's still this sort of ring-like structure. It's a bit like a Q. It has some kind of jet here. And this is a direct image coming straight through the gratings. The gratings also disperse the light, and what we see is an image of this same supernova in different emission lines as you move out along here, because they have different energies. And so this is an image in magnesium. This is an image in Lyman alpha, which is the basic hydrogen line. Neon 10 Lyman alpha, the basic line of neon 10. And then neon 9, and then oxygen 8 Lyman alpha. These are very, very highly ionized, hot elements in this supernova. So we can get a lot more detailed information with the gratings, but for those we have to have, we can only look at the very brightest sources. I couldn't resist showing you this picture just because it's so pretty. This is also a very famous nebula, the Crab Nebula, best known perhaps because it has the Crab pulsar in its center. Pulsars, when they were first discovered, the first one was called LMG1, for Little Green Man. LGM, I said it wrong. Little Green Man number 1, because pulsars pulsate extremely fast, milliseconds. And it was hard for anyone to believe that something that could pulsate that fast could have just happened in nature and hadn't been designed by somebody other than perhaps God. And in fact, it turned out that it wasn't a sign of intelligent life, that we've seen a number of these now, and they're very, very dense material, very densely packed neutron stars, and they're very small, so they can rotate extremely fast. The Crab pulsar is in the middle of here. This is also a supernova remnant that was expanded. And with this is the X-ray image, and you can see that it looks a bit like a spinning top. It looks as though this material is spinning around this axis here, and there's also appears to be some kind of jet with a little bend here. So it's a very pretty image, and I'm sure the supernova scientists are enjoying looking at that. We'll also be able to measure the velocities at different points to see whether it really is spinning with the spectral information we get. Okay, now I'm going to move outside of our galaxy to our nearest neighbor, the Andromeda Galaxy. And this is a galaxy very like our own. It's a spiral galaxy. It's a disc-shaped, and we're looking at a little bit of an angle. And the center of the galaxy is here. The center has a very big bulge, which is sort of spherical. If you could see it on its side, it would look extremely narrow with a bulge in the middle. But this isn't exactly edge-on. We're looking at it. This is the optical image of the Andromeda Galaxy. Again, you can see this with your naked eye if you know where to look. It's a little smudge in the sky. What I'm showing here is the X-ray image of the very center taken with Chandra. This is from a program by Steve Murray, one of the PIs, one of the instruments on Chandra, and he's looking, he and his collaborators, they're looking at this part of the Andromeda Galaxy every month over this year. I'm just going to show you a zoom in on that picture here. So I don't need to see the optical one anymore. An exciting discovery that Chandra has made is in the middle here, this is right in the very middle of Andromeda, there was one X-ray source with ROSAT. Now we see 5, 1, 2, 3, 4, 5 in an L shape, all actually quite similar in brightness. This particular image is done in energy space to show you that the red ones are the hottest, the ones with the highest energy X-rays, and the blue ones are the coolest. So this one here is very, very cool. It has many low energy X-rays, but not very many high energy X-rays. Much cooler than anything else in the picture. Now, Hubble Space Telescope has shown us that most, if not all, galaxies that are nearby that we can study in this way that have a bulge like Andromeda have a black hole in the middle. And the mass of this black hole ranges anywhere from 1 million to a billion times the mass of our sun. And the Andromeda galaxy has a bulge, so we expect it to have a black hole in the middle. You would also expect that since these black holes are about 1 million times the mass of what we call solar mass black holes, which are basically binary stars that we see in our own galaxy, then we'd expect that this black hole, like in the one Andromeda, will be much, much brighter than the ones we see in our own galaxy that are 1 million times smaller in mass. But in fact, as often happens in astronomy, that isn't what we see. We don't see what we expect. These are X-ray sources, all 5 of them. We don't know which is the black hole yet, but all 5 of them are embarrassingly weak. They're about the same brightness as the X-ray binaries within our galaxy. So we don't understand how this black hole, 10 to this, 1 million M suns, can be this faint. So theorists in astronomy have incredible imaginations. They have to have, because we're always finding things that we don't expect. So they're all working furiously on this, and I'm sure they'll come up with a very good explanation in short order. But right now we don't have one. We don't know which of these 5 is the black hole, but the best candidate seems to be this soft one, because it's highly variable, and emission that's coming from place very close to a black hole tends to be very variable, because you've got very, very extreme conditions and things change very quickly. And this is very variable. But we don't understand why it's so soft, why the X-rays are such low energy. So again, I'm sure the theorists will come up with an explanation soon, but we don't have a good one right now. Okay, here's another galaxy. This is the first active galaxy that I'm going to show you. An active galaxy is another name for a quasar, and this is thought to be about the nearest by quasar that we have. This is called Centaurus A. I'll just move it down here for a minute so you can see this. But this is an optical picture taken from the ground of this galaxy. And you can see it's very, very pretty, at least to my eyes and to the eyes of many observers. It's a big elliptical galaxy, so it's an elliptical shape. So if you look at it from any direction, it has physical size. And it has this huge dust lane through the middle. So you really can't see down into the core at all, because the dust is in the way. Now, stars shine because they're hot. Right? They're thermal sources. They shine because they're hot, just like the coals in your barbecue. Dust is cooler than that. So the dust blocks the light from the stars, and we just can't see it. This picture here is taken with a Hubble Space Telescope. And you can see that it has much, much better resolution. You can see all kinds of fine details in the structure of this dust here with a Hubble Space Telescope that you can't see in the ground-based image. So that's Centaurus A in the optical. And as I say, it's known as the nearest quasar. Now, quasars are the brightest things in the universe. They're the brightest steady sources, I should say. A supernova, when it goes off, can be as bright as a quasar, but only for a short period of time. The quasars stay that bright all the time. They're believed to be a supermassive black hole, so 1 billion solar masses or more in the middle of a galaxy. And that supermassive black hole affects everything around it because the gravitational forces are so great, it tends to suck all the material in. The material gets very, very hot, and we get a huge amount of emission. We get light of about 1,000 galaxies coming from a size of about a light day. And a galaxy is really, a normal galaxy is 30,000 light years across. So it's a very, very small region in which this energy is coming out. And you'll see in a minute why I told you all that. Here's the optical picture of Centaur again, Centaurus A again. Centaurus A means the brightest radio source in the Centaurus constellation, or Cen for short. So here's the optical picture with the dust lane. The dust, as I said, is cooler than the stars. If you look in the infrared, which is lower energy radiation, you're going to cooler material. It now looks very bright in the center because you're seeing the dust radiating in the infrared. But you still can't really see down through all that material and see the core. However, when we look in the X-rays, we don't see any of this stuff. All we see is a very bright source in the core, a little bit of diffuse emission here, and then a jet extending in this direction. So we're seeing right down into the core, right close to the black hole in the middle, the main energy source of this, of the active part of this galaxy. So that's what we see in the X-rays. And in the radio also doesn't see the dust or the light. It comes straight through. So in the radio, we can also look right down into the core, and we see a source right down here in the core, which is right close to the black hole. We also see the jets going out in two directions. This one is coming towards us. This is called the counter jets going away from us. These are jets of high-energy particles, very, very highly collimated. And then at some point, they disperse and produce what we call radio lobes. And the size of these radio lobes is much bigger than the size of the optical galaxies you can see up here. Now the X-ray jet is lined up with the radio jet, so it's the same high-energy particles that are giving us the radio emission and the X-ray emission in these sources. This just is a zoom on the, this shows the X-ray picture here and the optical underneath, the sort of bluish white shadows of the optical here and the dust lane through the middle. So you can see that the X-ray jet extends much further than the size of the optical image that we see of the galaxy. Now the X-ray and radio jet emission is not thermal emission. It's not emission because the material is hot like the coals in your barbecue. What it actually is electrons, which are charged particles spiraling around very strong magnetic fields. It's called non-thermal radiation. And that gives you both radio and X-ray radiation from the same material. Here's another picture of a big radio galaxy, again an elliptical galaxy. This is showing the X-ray in the red and white and the radio in sort of green here. And this is quite pretty. It looks as though the X-ray, which is diffuse material here, thermal X-rays, but very, very hot in the center of this galaxy. And then the radio is sort of bursting through this material. It seems to have cleared out the material here and here. So the radio is the non-thermal jets of high-energy particles. And it's cleared out a space for itself from the X-ray, which in this case is thermal, extremely hot, though, material. Okay, here's another further away quasar, 3C295. Actually, all the quasars I'm going to show you today are radio sources, though in fact, only about 10% of real quasars are radio sources. But the X-ray radio connection is quite an interesting one, as you will see. This is another big elliptical galaxy. It's called a CD galaxy. It's in the center of a cluster of galaxies, so it tends to be very big. It collects all the material that's loose and not in galaxies into itself. This is the X-ray image. It shows very hot material. This is thermal material right in the core. And then two, right in the very center, actually three, though you can't quite see it here, much brighter X-ray sources. The 3C is the third Cambridge survey of radio galaxies, and it's number 295. That's how we name these sources. This is Cambridge, England, though, the big radio telescope in Cambridge, England. Here's a zoom in on that X-ray source, shown in the background, the blue, and then the red is the very brightest part of the X-ray. And then on top, I'm showing you the radio contours. So we have a bright point X-ray source here. It's just a point source. We have a radio contour, but it's not very bright in the radio. We have a jet extending in this direction. This is coming towards us. We have X-rays and radio coming from this lobe. And from this lobe, which is going away from us, there's a faint X-ray source as well from this lobe. Excuse me. So this goes along with the picture that I told you before, where you have electrons spiraling around magnetic fields and giving you the radio emission. It's called synchrotron emission. It gives you the X-ray emission because the synchrotron emission, the photons, that is the light, interact back with the same electrons and just boost them up in energy, boost the photons in energy, and you get X-rays from the same material. And this we understand quite well, this particular one. The relative amounts of X-ray and radio emission fit the theories very well, and it's called synchrotron self-Compton emission. Another interesting thing we can do with this image, since as I mentioned before, we can tell what energy each photon of light, of X-rays has, we can divide it into the different energies. And this is the low energy image of that source here. And this is the high energy, which I will put on top briefly so you can see it's a different position. The high energy source is the point source in the middle, right in the middle of 3C2. Whoops, what happened to that? Oh, I know, so I've got a backing. I'll try that again. I don't have a view graph of this. It's funny, it's just a picture, I'm sorry. This is the lobe, and this is the low energy. So the electrons in this source and in this one here they've lost some of their energy. So you're giving you low energy X-rays. The core, which you see, which I can't show you, you only see in the high energy, still has very, very, very high energy electrons. So you see the high energy X-rays from the core and the low energy X-rays from the lobes. So again, that fits our theory quite well. Now I'm going to move much further from home to what was actually the first celestial source we pointed the telescope at. And the first thing you want to do when you have any kind of optics is to focus them. So you pick up your binoculars, you look at something, and you have to change the focal length to focus it on your eyes. That's true of the Chandra X-ray Observatory, just like any other telescope or binoculars. So we had to look at what we thought would be a point source, just a point of light, have no size to it, so that we could adjust the optics and make it as small as possible, and that would find our best focus. Well, imagine our surprise when we looked at this object, which is a redshift 0.6 quasar. It's known to be an X-ray source. Quasars are really, since most of the light's coming from the core, they're very, very small, particularly when they're a long way away from us. We can't see any size. They just look like point sources. This is what we saw, if you'll ignore for the moment these contours. We did see a point source right where I expected it, but we saw another source here as well. So everybody panicked. We thought there was something wrong with the telescope. Maybe one of the mirrors had got misaligned and launched and was pointing way off. This is 10 arc seconds away to the side. Or maybe there was some funny reflection off the back of the detector that was giving us a shadow on one side of the source. And so people were very worried for a short time, and they went through all these possibilities, and they found that none of these was occurring, that in fact we'd made our first discovery with our first celestial object. And that is, here we have the X-rays from the quasar, and here we have an X-ray jet. And we didn't expect to see an X-ray jet in this source, because in order to see a jet in this source, even if it's right in the plane of the sky, it has to be 100 kiloparsecs long. That's a parsec is 3 light years, so it's about 10 times the size of a galaxy. Okay, so in order to see a jet in the X-rays, it would have to be 10 times bigger than any jet we'd ever seen before. We weren't expecting that at all. So very, very exciting. We then arranged, since we know about this X-ray radio connection, we arranged for radio observations to be done. This is a source that's in the south. You can see here the name of it. There's a sort of telephone number type name. PKS stands for Parkes, which is the telescope, a big radio telescope in Parkes, Australia. And it did a survey. It's done a number of surveys. And PKS stands for the Parkes. And then this are actually the coordinates in the sky. So at 6 hours, and it's at minus 75. So that's in the southern hemisphere, a very, very long way down, minus 75. So we can't see it from the north. And the best telescope to look at it from the south is a new array that was built in Australia a few years back called the Australia Telescope Compact Array, or ATCA. So we arranged for it to look at this source, having found the jet in the X-rays. And the radio contours are what we see here, superposed on the X-ray image in white. And sure enough, there's a radio source in the core. There's a small jet here, which lines up beautifully with the X-ray jet. At this point, the jet stops and takes a little bit of a turn. This is seen quite often in radio jets. It probably hit some denser material here, which affected the magnetic fields and the particles in the jet and deflected it. This is also the point at which the X-ray emission stops. We don't exactly understand why. There's also a counterjet in this direction. We don't see X-rays from that, but that's probably going away from us, so it's much harder to see. I have a very highly processed X-ray image of the X-ray jet here. This was generated by adding together. Of course, we looked at this object a lot to focus the telescope. So there were quite a number of observations that are quite close to the best focus. And scientists, both at the Chandra X-ray Center and also at Penn State, worked together to produce this image, which is a summation of lots and lots of pictures of the object. So we get very, very sensitive picture. And so here's the quasar itself, the core, as it's known. And we can see several different knots here, which we've labeled A, B, C, and D as we go away from the core. And these actually also line up in detail with knots in the radio. So that's what it looks like. We can't explain the X-rays from this jet. Once again, astronomers see something that they don't understand. There are about 2 orders of magnitude more X-rays than we expect to see, given the amount of radio emission that's there. And so it's a long way from what we call the equilibrium equipartition model for the synchrotron self-Compton than we expect. So we're still working on that. Again, there are theorists with a lot of imagination working on it, and hopefully they'll come up with a solution pretty soon. But it's very exciting. Okay, now I'm going to move on in closing to a few different kinds of sources. This is a cluster of galaxies. As I mentioned earlier, galaxies like to cluster together. They tend to form in groups and clumps and also very, very large collections. This is a very large galaxy cluster. It's called Abell 1367, after Abell was an astronomer who did a catalog of extended sources, and this was his 1367th one. And you can see, if you look carefully in this optical image, lots and lots of sort of fuzzy blobs. Some are very flat. They're disk-like galaxies like our own, like this one here, and this one here, and this one here. Some of them are elliptical. Some of them you can see spiral arms. There's masses of them. Very, very pretty picture to study in the optical. In the X-ray, it looks completely different. We do see a few of those sources, individual sources in the X-ray. Here's one, here's another. But mostly we see just this huge diffuse blob of very hot material, gas, right in the core of the cluster. So in order to understand how much material is in the cluster, we need to not only look at the galaxies, which give us optical light, and there's obviously a lot of material in the galaxies, about 100 billion stars in any galaxy. But we also need to understand how much material is not in galaxies, and that's what the X-rays show us. And only then are we seeing perhaps most of the material in a galaxy cluster, but there may still be dark material that doesn't give us any emission. So to get a complete picture, we really need to see the optical and the X-ray. And by studying the amount of material as a function of distance and also its velocities, you can measure the potential well, which actually measures the real mass of the cluster. We also expect to find, in the X-rays, to find high redshift clusters, so clusters a long, long way away from us, much better than you can in the optical, because in the optical you've just got individual sources. So we expect to, a lot of our deep surveys, which I'll move on to now, to find new clusters. And it's important to count how many clusters we see at higher redshifts. That actually can tell us a lot. Since they're the main building blocks of the universe, it tells us a lot about how galaxy clusters and galaxies themselves formed and how the universe evolved over time. So the other kinds of science that's a really big step forward is to do surveys. Whenever a new instrument comes online that can look much deeper, we do surveys. That's part of the job of being an astronomer. We just look and see what we can see. And there are 3 very deep surveys that are being done at the moment, and initial results are coming out from them, mostly by guaranteed time observers. These are people who've worked on the satellite and get given time as a reward for all the work that they've done. This does not include me. They're people who build the instruments rather than people who work at the X-ray Center. I'm actually working on a somewhat different survey that is not going to go as faint, but it's going to cover a much larger area of sky, so we can see many more of the brighter sources than can be seen in the deep survey. So it fills a gap between the deep surveys with Chandra and the deep surveys that are nowhere near as deep with other satellites. We've called this CHAMP for the Chandra Multi-Wavelength project. And this just gives you an example of the kinds of things we do when we're doing a survey. This is an optical image that we took on Mount Hopkins in Arizona with a telescope out there that belongs to Smithsonian. That's in the background. And then the red shows you the contours of the X-ray sources in that same part of the sky. This is an image that's about 100 kiloseconds long, so it's fairly deep. It happens to be centered on a cluster of galaxies. So again, we see, in the optical, you see lots of white blobs. These are the galaxies. And in the X-ray, you see this just big diffuse blob, which is the material in the middle of the cluster. For the survey, we're not very interested in that. There are other people studying the cluster. They're the ones who pointed at it in the first place. We're studying all these sources further out. And to give you some idea of the fact that you see different things in the optical than you do in the X-ray, there are many optical sources here for which there is no X-ray emission at all. Stars don't give you any X-ray emission at all, really. They're mostly thermal sources that you see in the optical and perhaps the near-infrared. But then there are some optical sources, like this one here. You can see a white dot in the middle of the red contour. Here's another one. Here's another one. Some of those X-ray sources do have optical counterparts. So there's something like a quasar that's giving you optical emission and X-ray emission. Then we have X-ray sources here, 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 where there's no optical counterpart. Here's another one. Here's another one. Here's another one. And these are very interesting sources because we haven't seen them before. We have to look in the X-rays and look very deep to see them. What we think they might be is absorbed quasars. So quasars where you've got a lot of material that you're looking through between the black hole at the center and us. So we're looking through, it's like looking through the edge of a galaxy when you look through all the disk. As in Sen-A, you couldn't see the core. These quasars, we think we're looking through a lot of the outer material. So in the optical, you can't see much anymore. All that light is absorbed by that material. But in the X-ray, which can get through all that material, you still see it. So we think these are absorbed quasars. We have to look more and harder. We have to go look in the optical, look deeper, see if we can find them. We have to go look in the infrared, see if we can see them there, where they wouldn't be as absorbed, to prove that. But this is what we think they are. And another reason for doing surveys is one of the first things that were discovered in the X-rays by the first balloon X-ray mission was, it's a rocket flight, was the X-ray background. And what that is just diffuse X-ray emission from all over the sky. They started out thinking it was noise in their detector, but it turned out it really was a background in the sky. And as we look fainter and fainter, we find more and more of the sources that go up to make that background. And a big question has been whether that background is made up of many, many, many sources, and that's it, or whether there's a real diffuse component, a bit like the diffuse component in the middle of clusters of galaxies. If there is a real diffuse component, then it could close the universe. There could be enough material out there that we've never seen before to actually cause the universe to stop expanding and turn around. Not in our lifetime, so don't worry about that. But it's a big question whether the universe is open or closed. So far, the deep surveys seem to be showing us that about 80% of the background is actually from individual sources, not from diffuse material. So it's looking as though we're going to see most of that background in individual sources, and we won't be able to close the universe. But we'll see. As time goes on, we'll find out more. Okay, so I'm going to close by showing you our website, in case any of you are interested in more pretty pictures. And all the ones I showed you today are on this website. The address is quite easy to remember. It's chandra.harvard.edu. And the Smithsonian Astrophysical Observatory is located in Cambridge and is part of Harvard University as well. We're sort of, their astronomy department is blended with us, hence the address. And this is the top page and what it looks like. There's some history of Chandra Sekhar here. This image changes with time, just the latest pretty image. This is a Supernova Remnant, a different one from the ones I've shown you today. There's a link to the astronomical community support, user support here, which is the page that I mostly am associated with. There's information about the launch. There's various stories and news bulletins. There's also crossword puzzles and kind of activities for your kids to try out, and classroom activities and that kind of thing. So it's actually, this site has won awards for being a good site. I can say that and boast about them because I have nothing to do with it. That's the education and outreach people who control that. So I'll just finish with a montage, because it's pretty, of the satellite here, again with a nice nebula in the background, and some of the images that we've seen today, the Crab Nebula, is the center of Andromeda, is 3C295, Cassiopeia A, and then several that you haven't seen. And I'll close there. I also have some handouts, which I'll put on the steps here if any of you would like to take some of the pictures home, and a little bit of information with you. Thank you.
Thank you, Belinda. We have some time for questions, if there are any. Yes.
What's the mechanism for the production of the X-rays and the X-rays that the
It's thermal. Maybe I should repeat the question. What's the mechanism for the production of X-rays in the center of the clusters, right? The diffuse X-rays. It's actually thermal emission. It's radiating because it's hot. But in order to be hot enough to give you X-rays, it's extremely hot, sort of hundreds of thousands of degrees. That's so hot that you don't see visible light from that. It's only hot material. Okay, the gas is so hot that it's not giving you any visible light. It's only giving you this very, very high energy light, which is actually quite low for X-rays. It's low energy X-rays, but much, much hotter than anything you could see in the visible. So you see the very, very hottest material.
Question back there.
What is it? The question was, what is a jet? What we think it is very, very strong magnetic field that extends, we don't know why, extends over very large distances. And then you get high energy particles that are generated close to the black hole, just because everything close to the black hole gets so hot. Everything's moving very fast. And then some mechanism sends these particles out along the magnetic field. And as they spiral, the electrons, because they're charged, spiral around the magnetic field, and they give you radiation called synchrotron radiation. It's polarized radiation, so you can tell that's what it is. And then the radiation that's coming from those electrons is photons, right, X-ray photons. They interact again with those same electrons and get boosted. So the initial synchrotron is radio, and then when it interacts again, it scatters. It's called Compton scattering. Then you get X-rays, very, very high energy material. But really what it is just particles streaming out along a magnetic field, and the magnetic field keeps them collimated.
Yes.
Yeah, the main X-ray detector is called the ACES. It's a CCD detector, actually very similar to that you would have in a digital camera. But it's read out very differently. because an individual X-ray photon has so much energy it can fill a well. If you know anything about CCDs, they have wells. And optical photons, you can get lots of photons in a well before you need to read it out and saturate. X-rays, you can't. So we read it out every 3 seconds. And even that isn't fast enough for all our observations. So we have techniques for reading out bits of it faster for the really brightest sources. But they're CCDs. Yes. Yes. Spiral galaxies. Because they're rotating very fast. It's like, I mean, if you, yes, yes. And if, you know, the solar system is the same. The sun is in the middle and all the planets are out along a plane because they're going around. So it's just the angular momentum of the rotation keeps them from moving in one dimension, or 2 dimensions, I should say. You mean in the universe as a whole? It's random. The plane of rotation for an individual galaxy is not random, but one compared with another, they are random. If you remember the picture of the cluster of galaxies you saw, you know, them at different angles on that picture. So they're random with respect to one another. Some of the, yeah, we think some of them are. I mean, it's hard to know for sure. Yes, it could. In fact, that's one of the theories why only 10% of quasars are actually radio sources. And we don't really understand why. Some people think there's maybe material blocking the jet from getting out. But another theory is that the radio galaxies are the ones with Kerr black holes, which are the ones that rotate very fast. And the quasars without the radio source have what are called Schwarzschild black holes, which don't rotate very fast. So that's one of the theories. We don't know for sure. Not yet. It might. It's hard to be sure. I mean, certainly we can see further away in the X-rays than we've ever seen before. But some of those sources have already been seen in the optical, or could already be seen in the optical, in which case we're not going any further. But some of the new sources we're seeing, like the ones I showed you in that picture, could be at very, very high redshifts and extended. We don't know yet. You know, we have to actually measure the redshift. To measure the redshift, we have to see a couple of emission lines and see what wavelengths they have. So we need more information than we have. So maybe it already has, but we don't know that it has yet. Yes. Yes. Yes, it has. On our galaxy, I suppose eventually they could merge. It is moving towards us. It's what's called blue shifted, but at a very small velocity. So it would take very, very, very long time. But galaxies do often merge together. And in fact, some people think that quasars are caused by 2 galaxies merging, moving together because they pull at one another because of the gravity, and merging together and creating the black hole in the center. So that's one of the theories for how at least some of the quasars that are out there form. So possibly Andromeda and the Milky Way will one day merge. I don't know, but it'll be a long way in the future, not in our lifetime. About 10 years. We have funding for 10 years. The orbit won't decay for about 20 years. But probably other things will go wrong in the meantime. Yes, it's very, very far away. It's thousands of miles away, so even at the innermost point. So we can't service it now.
Question here?
Well, originally it was going to be launched on a rocket, and there were lots of redesigns. I think in the end it ended up being cheaper to do it this way. And also the fact that people will be up there to let it off, some people thought that was less risky, you know, that it was actually launched from the shuttle. But it did have problems because then we had to make it small enough to go in the shuttle bay and light it. We had to cut down on the weight and that kind of thing. So, but it went through a variety of designs before it actually came to a final design, mostly because NASA cuts budgets continually.
How do you calculate the distance of objects from the X-ray? You have the optical, you have standard, thermal, and maximum.
Right.
Is there a
So
counterpart?
a good question. No, not really. I mean, we understand the optical universe much better than any other wavelength because we've looked at it, obviously, for much, much longer. So in order to measure the distance to a quasar, the best way is to go and get an optical spectrum and find the emission lines. If we can see X-ray emission lines, which we can in some of these sources, we see a big, strong I and K alpha line, and we measure the energy of that, we might be able to get a redshift. But the energy of that also depends on the ionization of the material. It gets higher energy as the material gets hotter, so there's much more uncertainty. So there are ways, but at the moment the optical is our best way to measure distances. And we don't have standard candles the same in the X-ray yet.
Yeah, I think one last question here.
The accuracy of the mirror surface. You have to have the mirror surface accurate to a fraction of the wavelength that you're looking at. But actually, we're helped in the X-rays by the fact it's grazing incidence, so it's actually the cosine of the angle coming in. The accuracy has to be that good. But it's basically accuracy of the surface. So that mirror was polished and polished and polished and polished. And thanks to the telescope scientists, who was Leon van Spaebroek and Perkin Elmer, who were the people who did it, we have this exquisite optics. There are two pieces. There's a parabolic and a hyperbolic to each mirror. So there's actually 8 mirrors, if you like. There's 4 hyperbolic and 4 parabolic. And the X-rays hit one of them first and then the other, and then focus on the detector.
Okay, well, thank you all for attending. There are some handouts up here for those who wish them.
Yeah.
Some steps.
Put-
So let's move along to the subject of our lecture. So let's move along to the subject of our lecture for tonight.